going to report my recent findings in, or results, better maybe, not findings, but findings on diffraction by wedges. So I will talk about electromagnetic diffraction by right angle wedge. That was published 5 years ago. Then one of the 3 problems will be acoustic diffraction in a semi-infinite waveguide that just published. And briefly, I will discuss acoustic diffraction by exterior of a right angle wedge that actually I derived here during this excellent during this time using excellent opportunity provided by the institute. All right. So the first problem, it is acoustic wave propagation in semi-infinite waveguide with flexible walls. So it means that we don't just simply have acoustically rigid or soft walls. They membranes and may change their shape because of acoustic pressure. So most closed results were obtained by Kuzov and Pachin in 1976. They considered the same, by the way, problem, but with elastic. So this guy disappeared. Okay, so they considered elastic walls and derived integral representation, quite complicated, didn't analyze existence uniqueness, and didn't derive a solution in a form convenient for computations. But what great of this paper was that they actually found use the same essentially integral transformations that I will discuss later, and also notice that if the differential operator with respect to variables which change along the walls of even order, mainly like elastic or membrane or high order, then the solution principle possible to derive. Allori and Abrahams considered this a problem, but when vertical and one of the walls was acoustically rigid or soft, I think it was only acoustically rigid, then by continuation you can convert this problem to the problem for whole strip. And in joint work with Focus, we considered rigid walls, but the boundary conditions were more complicated nature upon Carré boundary conditions of the first order. All right, so what we have mathematically, the problem can be formulated as a Helmholtz equation. The boundary conditions of impedance type, but because we have walls which are membranes, then we have additional operator. You see, in each boundary condition, in the brackets, we have additional operator. That depends on x. If x varies along the from 0 to infinity, this with respect to x, again with respect to x, and this on the vertical wall with respect to y. H conditions, we assume that they clumped the wall. It's natural boundary conditions. Membranes are joined, and if we express pressure and deflection through complex potential U, then we'll have these formulas. So basically, if you know U, we know everything about the physical problem. So the idea is to use a Laplace transform in two variables, but normally if you have two variables, you use Laplace transform with respect to one variable and Laplace transform with respect to second variable, and the parameters are independent. In this case, we apply the Laplace transform. Since the boundary conditions on when x equals 0 are quite complicated form, we shouldn't expect that we will solve the problem. We will have a right-hand side that is unknown. It's because of the point x equals 0. And that function f is expressed as a function and its derivative. And as soon as we know these two functions, we know, of course, the solution. But we need to find them. So if we introduce two functions, mu j tilde, mu1 and mu0 and mu2, I believe I call it, then we can a little bit simplify the boundary conditions. I already simplified here. But it's still a function. It's not a constant. It's a function of parameter. Now, if we use this, if we write the solution using green function, then we have a very simple formula. But again, don't forget that f is unknown function. Now, if we fix y, if we fix y and y equals 0, then apparently the green function will be fixed, and then we will have exponential function, but without y. And that is also looks like Laplace transform, but the parameter of the Laplace transform is zeta. Zeta came from the ordinary differential equations that we had from the first integral transformation. So that is why the second Laplace transform with respect to variable y has a parameter that is not arbitrary parameter. It is a function of eta. So it's not like we just guess it. It's naturally appears from the solution. So zeta is, it's probably previous slide. Zeta is, it's a single branch of multi-valued function. And we fix in a way that the real part is positive on the real axis. That is why we will have an opportunity to write a solution in a simple way. I mean, which doesn't grow at infinity. All right, so that is basically the idea. Now, we still have lots of unknowns here. But we have a boundary condition on the vertical wall that it was not used yet. So, as I said, if we fix the y equals 0 in the solution, in this formula, then the g function, the green function, becomes exponential function here everywhere, and then can be expressed through the Laplace transform with hat, with respect to this y variable. And that is why we will have some additional formulas. Also, since we can apply the Laplace transform with respect to x with minus eta, then we will have another formula with minus. And also, we can do it with another wall, because we have two walls, horizontal walls. So that is why we have four relations. One relation is on the horizontal line, second one, low horizontal line, second on the upper vertical horizontal line. And also we can change eta by minus eta, and now we have four relations. So it is, of course, and so far we didn't use boundary condition on a vertical wall, or finite vertical wall. Now, of course, we can invert these relations. So if we introduce these notations, then we can invert these relations and remove, express the functions with zeta through these two nice functions, plus minus eta 0 and a. I didn't write them, but it's possible. Because we have 4 relations, we can, of course, invert them. Now, the boundary condition on the side x equals 0, on other word, a vertical line that is finite, we apply the Laplace transform to this boundary conditions also with the parameter I zeta. And we can do it with plus zeta and minus zeta, because it is a finite segment. So, and we can do it without any restriction, because we don't care about the growth, possible growth. It is finite interval. So that is why we have 2 more conditions. And I remind you that these 2 functions can be expressed through the function with eta and plus minus eta from the previous slide. And then if we substitute them into this relation, we will have 2, actually it will be in general, matrix Riemann-Hilbert problem. So if the boundary conditions in the very beginning were more general type, I mean not like membrane, but more general boundary conditions which have not only second derivative but a first derivative, everything, then of course that matrix then will be a very complicated matrix Riemann-Hilbert problem. So it could be probably 1-2 pages in order to write this matrix. But as soon as they even order, I mean with membrane or elastic, then immediately it simplified and become diagonal and separable. So very simple. You see, these 2 problems are scalar Riemann-Hilbert problems. But since we used that definition, we replace eta by minus eta, we deal with 2 functions, and you see plus minus eta. So that is why the solution of these 2 simple problems needs to be found in the class of symmetric functions. So in addition to just properties that they are analytic in upper and lower half planes, we need to have the solution which satisfies these extra conditions. And that's actually not a big deal. Yeah. Now he also wants to emphasize that the coefficient of these 2 simple Riemann-Hilbert problems is a rational function and has information about only the vertical wall. That impedance parameter alpha 0 and alpha 1, of course, it's in the right-hand side, but not in the kernel of the Riemann-Hilbert problem. Now we factorize it. It's not a big deal. But since it's a rational function, you have a polynomial, you see degree 3, we should expect that the zeros of this rational function in poles depend on the parameters. And it actually happens. We have 3 possibilities. It is possible to prove analytically that there are either these poles on 0 either in opposite half planes, or one of them in real and other opposite half planes. I mean, 2 of them in one plane and one in the second one. So there are only 3 cases. So for these 3 cases, we have different solution, of course. And that is some kind of first physical anomaly that I found, that is, at least in diffraction theory, it is known, not known, that you have a uniqueness. You have, depending on the parameters of impedance parameters, you may or may not have extra constants. And of course, it's because of the flexibility of the walls. All right, so we derive the solution, and it's a Cauchy kernel, and H plus, that is also a rational function. It is easily possible to verify the symmetry conditions. The solution we found satisfies these conditions, and decay in a way that we expect. And the solution, as you see, has the same form, but in one case, do I have a constant? Yeah, it is constant bj. So that depends on the index of the problem. So there is either both 0 or one constant if one of the poles on the real axis is there but is uniquely defined, or these constants are free, 2 constants free. Then, of course, we need to recover all the constants. Also, we had several constants, 4 constants, which came naturally from the it's not because of index, but because of the boundary conditions. When we apply Laplace transform at the corners, we had second derivative of mixed second derivative of the potential, and if we approach the corners, the two corners, on the one side or another side, we have two different constants. So this is why we have four constants. So two constants is easy to recover because we just use the boundary conditions on the horizontal walls, fix it, use the residue theorem, and they found. The other two, a little bit harder because you need now to work with this form. And we live in the eta plane, but this functions depends on E zeta, and zeta is a branch of the function. So that means that we need to, if we use an inverse Laplace transform, we need to integrate with respect to zeta. And then we have, since this function depends on the solution of the Riemann-Hilbert problem, which depends on the eta, so we will deal with multi-valued functions at first glance. But it turned out that this combination, phi plus eta minus phi minus eta divided by eta, is single valued in a zeta plane. So no Riemann surface. That is why I always look at suspiciously when you have a plane and then say, wait, we integrate it using the Riemann surfaces. It means that it's something probably not accurate. So here we don't use any Riemann surface. We just we still live in the same eta plane because our solution is single valued. Although eta is a single valued, it's a branch. This has a branch point, this branch points, eta with respect to zeta. But since we divide by eta, regardless which branch we deal with, that function is analytic. And then we can use analytic continuation and residue theorem. It's quite technical, long, but still found. So that is these graphs, of course, I will not discuss long because it's time, but they show that method works. And then we have a solution that is reasonable in the plane and continuous in the corners. And that is only for the case 3. The case 3, I remind you, when we have two extra constants, B0 and B1 and B2. And so for some parameters, we have two more constants, and for other parameters, we don't. So it means that these two constants can be used in order to achieve that the pressure at the two edges, two corners of the half strip is continuous. In the second case, when we don't have B1, B2, three constants, pressure would be discontinuous, but it's a model. It's a, I wouldn't say something. Yeah.
Sorry about that. Could you say again, after you solve the Riemann-Hilbert problem,
yeah,
how do you reconstruct the field, the original?
Oh, because phi, these two potentials, the solution of the Riemann-Hilbert problem, it's a Laplace transform of U on the sides. So we use inverse Laplace transform. We have the solution on the sides, but then if you know the function on the boundary, and we also know the vertical boundary, now basically what? You can use just a green formula, for instance, because you know the function, you know its derivative on the boundary, or lots of different opportunities to find the solution everywhere. But in fact, I just computed only on the boundary. I didn't use it again. All right, so it's also some graphs. So now, second problem. So second problem, more complicated. It is electromagnetic diffraction by concave wedge. And it is coupled diffraction problem. So we have electric field, magnetic field, and the incident wave strikes the wedge at oblique angle. Means that there is one angle. If you have actually two angles here, so it looks like if you have a wave, so it's possible to strike orthogonal to the edge, but at certain angle to one of the planes, but also could be angle to the line between these two planes. So there are two angles, beta and theta 0, which show that this wave obliquely strikes the wedge. And if beta is pi over 2, then this electric and magnetic fields are separated, and it's problem solved as an acoustic problem a long time ago. But if it's not, then the problems are coupled, and it's quite complicated. So it's a brief history. Again, as I said, scalar cases were considered by Maluzhinets, Senior, Bernard Lyalinov. A vector case, there's only one, to my knowledge, solution for a vector case, but it's only for half plane. Then it's a Geno 3 Riemann-Hilbert problem by myself and Silvestro. Then lots of approximate solutions, of course, for the vector case. Myself and Lyalinov, Zhu. Numerical matrix factorization by Daniele, Lombardi, and so on. So the idea here, the goal of this work is to find at least one non-plane structure which is possible to deal exactly. So again, now model. We have electric, magnetic field. It's an incident wave. Then, as I describe in this way, it's convenient to use these notations. Then there's Maxwell equations, which connect Z and rho, it's radial, and the Z components of electric magnetic field. And if we use this connection and substitute into the impedance boundary conditions, then we will have two Helmholtz equations. Helmholtz equations come from Maxwell equations. And if beta, as I said, pi over 2, then these two problems are separated and can be solved in relatively, at least in known way. But if beta is not 0, then you see these two functions are coupled by boundary conditions. And of course, Maxner and radiation conditions. Again, the same idea. For half a wedge, that idea was actually first reported by Vito Daniele, but he didn't even derive the matrix Riemann-Hilbert problem. But in 2003, he actually suggested to do it and said it would be possible to solve the problem. So this idea, again, similar to what I used in the first problem. But now two walls are semi-infinite. We have semi-infinite wall, horizontal and vertical. We don't have half a strip. So I will just briefly say that again, we apply Laplace transform. We have now two functions which are known and expressed through the function and this derivative. Then if we don't use the boundary conditions, then just only based on this Helmholtz equation, we can write two relations for phi and psi, phi 1 and phi 2. And if we replace eta by minus eta, we'll have two more. So if we try to use the same terminology as analysis focus uses, it could be considered like global relations because there is no information about the boundary conditions. So based on these four relations, now we complement them by boundary conditions and see what happens. If we do it, then we have more conditions. In fact, at the end, if we count all, we have 8 unknowns and 6 unknowns. 2 functions. Yeah, so anyway, we have two more conditions. We have more conditions that we need. So in this two more conditions, we'll, not we need, of course, them, but that we have, after we play with all these boundary conditions, we have two extra conditions which constitute a 2 by 2 Riemann-Hilbert problem. And that is a Riemann-Hilbert problem. Now, I wrote here two Riemann-Hilbert problems. The reason is we have two choices. We can apply the Laplace transform, the basic Laplace transform with respect to eta along the horizontal line first, and then we have extra functions with respect to zeta, that is a function with branch points, along the vertical line. Or we can apply Laplace transform along the vertical line and then use have these functions with zeta that we want to eliminate along the horizontal line. So, and it turned out that we need to work with two of them. And I will briefly mention at the end that it's very important because it helps to eliminate extra conditions, extra constants, sorry. So, but we don't need to solve both problems. We need to solve only one problem because there is a simple connection between the solution of these two problems. If we replace one parameter by another one, with vertical line by horizontal line, and angle beta by pi minus beta, and also here also just make this replacement, then the solution of the first problem becomes the solution of the second one. So mathematically, we need only one problem. Right, so I didn't think write the G eta, but it's written here. G eta admits this relatively simple representation. We have a function, we can put it aside. It makes the determinant of the rest is 1. You can always do it. Then we have one polynomial function, another polynomial function, and zeta. That is everywhere in the problem, in the previous problem, square root x eta squared minus k squared. And basically, any matrix factorization is based on a diagonal factorization or scalar factorization. So if we want to do it, we can just diagonalize a matrix and look what will happens with the matrices, transformation matrices. If they're not analytic, then of course it doesn't work. But if we restrict ourselves to matrices, I call them T matrices, which transformation matrices. Like if you have G, that is T minus 1 diagonal matrix T. So if these two-valued matrices, and since we have 2 by 2 matrix, then we can reduce the problem to a scalar Riemann-Hilbert problem on a Riemann surface by forming a Riemann surface according to the branch points of the matrix T. So if we look at this problem based on that idea that we did with Sylvester, then we'll have the same matrix that derived by Chebotarev in 1956. He didn't use Riemann surface, but he just asked the following question: what is the most general form of 2 by 2 matrix which compute with its right-hand side? And it's very important in order to apply the just Cauchy integrals and write the solution. So, and then Hrabkov derived the formulas for the case when the factors don't grow exponentially. Using Riemann surfaces, it is possible to remove it. And that idea was first reported by Moiseev, but again, his approach was just to remove that exponential growth. I will discuss it later. We did it from different side, and all these approaches give the same matrix. There is no possibility to find something more general than this matrix. The matrix actually will be in the next slide. Sorry. But anyway, I want to stay a little bit at this slide because the function d of eta is very important. It is a rational function. It's a determinant of this matrix G. And again, we have similar situation as in the previous problem. There are some zeros, poles, and they depend on the location of the impedance parameters. So that is why we should expect again dependence of the solution with of this index. It's the total index of the problem. Now that is a matrix that I mentioned. G of eta has a structure. So if we remove the polynomial matrix and then we can write the matrix gamma that has, so this everything that is here scalar, that is G1 of eta, is a polynomial matrix, and that matrix has a structure. That is a that is known as Chebotarev-Khrapkov matrix. So that is Helder, unit matrix, polynomial matrix with this structure. So if you have just arbitrary polynomials here, it's still always possible to have L minus L. And the method is first find the degree of the polynomial. It is of degree 8. So it means that the future Riemann surface will have genus 3. And we construct the Riemann surface in the following way, standard way. We have a hyperelliptic surface. That polynomial, the characteristic polynomial of, not characteristic polynomial, the function, polynomial function that on the previous slide of degree 8. And that is why we have a genus 3 surface. And our goal is to factorize the function on the Riemann surface, which coincides with the first eigenvalue on the first sheet and second eigenvalue on the second sheet. So that's eigenvalues of the matrix gamma. So if you summarize the result by myself, myself, and Silvestrov, and focus them on the problem at hand, then the strategy or the method can be summarized and be written in this theorem. We need to find the solution of this scalar Riemann-Hilbert problem with a coefficient that, again, on the Riemann surface on the first sheet L1 and second sheet L2. And then the matrix, the factorization can be written in this way, where Y is this matrix and Q is polynomial matrix we introduced before. Oh, actually, there is no Q here, just one. Oh, yeah, Q is here. All right, so now we need to solve this problem. Originally, I worked with a different approach, and Alexandra suggested that it could be approach which, and the approach that I will discuss later is largely depends on Jacobi inversion problem. And he suggested to use the Baker-Kaiser function. It is a very powerful tool using integrable systems, and it actually goes in a little bit in a different direction, because up to a certain point we don't need to Jacobi inversion problem. But when we apply the Liouville theorem, we need the zeros of this Baker-Kaiser function, and basically it's also a solution of Jacobi inversion problem. So in some sense it's equivalent. But Alexander believes, and I share his belief, that it's possible to bypass Jacobi inversion problem. And the reason for that is that another, not equivalent, but similar problem of scalar Riemann-Hilbert problem on circular domains in 1978 by Chibrikov and Silvestrov was found approach for Riemann-Hilbert problem on a multi-connected circular domain, which actually bypass a Jacobi inversion problem. And by constructing the analog of a multiplicative analog of Cauchy kernel, they complete the solution of Riemann-Hilbert problem, and I don't know what needs can be done in addition. So everything was done by the end of the 70s. All right. So that is why, of course, that idea that they used not directly applicable here, but still, since they, in some sense, if not equivalent but similar, it is possible, I believe, at some point, somebody, if not us, find a way how to avoid Jacobi inversion problem. But how this Jacobi inversion formula appears? We want to factorize this function lambda. I remind you, it's a lambda 1 on the first sheet, lambda 2 on the second sheet. So naively, we can write this, well, like in a complex plane, exponential function of a Cauchy integral. Of course, on a Riemann surface, there is no Cauchy integral. It's analog. Analog is a Weierstrass kernel. Oh, there are lots of analogs, infinite number of analogs, of course. One of them, and most often used, is Weierstrass analog of the Cauchy kernel, is this one. But you see, because W is algebraic function, and I remind you, in our case, it's a degree 8 polynomial, so there is a growth here. And since f degree 8 polynomial, W grows is order 4. And then if we take exponential function, then of course we have essential singularity. And to remove it, we cannot just work with this simple solution. Also, we have a beautiful symmetry here. So if we write this formula in a complex plane, so you see, if it's a log, due to this nature, if you write in a complex plane, we will have log lambda 1 plus lambda 2 and log lambda 1 minus lambda 2, log lambda 2, because there are quotient and the product. But product is identically 1, so one integral disappears, and we end up with only lambda 1, lambda 2. If we study the indices of this function, lambda 1, lambda 2, because of the symmetry, there are two possibilities. They could be index minus 2, 0, or plus 2. All right. Now, yeah, and we want to remove this growth. To remove this growth, we can add, first of all, integrals over A, B cross sections. Here it shows only A and B cross sections. Because of symmetry, you see, it's what I found here, that because of symmetry, we don't need to deal with we can actually confine ourselves to the genus 1 representation in some senses. Of course, symmetric, if we spread it, it will be still like genus 3 representation. But symmetry is everything converted. We don't need more A and B cross sections. In general, we need 3 of them, but now it's only 1. And when we write this solution, these integrals will not contribute to discontinuity. This integral also, because we don't have here any functions, it's just pure analog of a Cauchy kernel. So the discontinuity is just multiple of 2 pi I. When we take exponential function, because the solution is exponential function of this function, this 2 pi I k will not contribute. That is why we can add these functions, will not damage the structure of the solution, but then we have a chance to remove the growth of the whole function at infinity, because now we have W here, W here, W here, and if we analyze the behavior solution, we end up with Jacobi inversion problem. So that is a original condition at infinity. If we make some adjustment, there is a nice book on elliptic functions, but anyway, so then it's operated maybe later on. Anyway, it is not directly, I mean, the integral is not directly in canonical form, but we can do it, and eventually we will find the solution of this problem. In fact, it's not even Jacobi inversion problem, it's just a problem of an inversion of elliptic integral. That is quite simple. When we have genus higher than 1, then it's a problem. Then we need theta function, and so here it's just a simple exercise. All right, so now matrix factorization, we use the formulas written before, but now we return from the Riemann surface to the complex plane. Everything is fine, and in fact, if you think of that, it's just like integral of complex plane without any A-B cross sections and so on. It's just Hrabkov formulas. But these ingredients quite complicated because we have some something that came from Riemann surfaces. Yeah, and remind you that second index appeared that relates to index of eigenvalues of the matrix to be factorized is k0 also appears in the solution. Now we have 2k. One is a total index and then an index of eigenvalues. But they connected because of the symmetry. So that is the solution of Riemann-Hilbert. Yeah, and you know that in any Riemann-Hilbert problem, the last step is to apply the Liouville theorem, and that you need for that you need to know the structure, or I mean the properties of the solution. I mean the behavior at infinity, the possible poles and zeros. And zeros and poles come from the solution, since we had exponential function when we factorize the eigenvalues, and those functions had some logarithmic singularities because of the single integrals involved. Then those logarithmic singularities, when after exponential functions, become poles or zeros. So everything needs to be counted. And when we write everything carefully, then we end up with a general formula of the solution. And that is it. We have R, that is a rational function, and all the ingredients are known. And some of them came from the, everything came from factorization here. And yes, you see this k0 is the index of the eigenvalue. It's also here. All right. Now, one of the, if not the most complicated, but still a very complicated step. Remember, our solution has to be symmetric. And initially, it was just phi plus equals phi minus eta. But now, you see, that is phi plus. If you write phi minus eta, then you need to put eta everywhere, minus eta, here, 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 everywhere. And all these functions are not symmetric. So if that solution is not symmetric, then we need to put it in a bin. So yeah, this is phi minus. You see, that function and that function, when we make substitution here, eta by minus eta, that function has to be absolutely the same. Not at any one point, everywhere in the plane. And for that, we need to work with the symmetry conditions. Symmetry conditions, when you write it in, I mean, when I wrote it first time, I thought, yeah, so there is no hope to satisfy this condition. Because you see, that is the integrals on a Riemann surface. It's nightmare. Here's a polynomial matrix, quite complicated. And again, canonical, and they not compute. So, but it turned out that everything can be sorted out. For instance, if we carefully write the factors and that polynomial matrix and then satisfy this condition, it's long, of course, but it is possible to prove. Then it means that that condition equivalent to a simpler condition. So we deal with, we need to prove that p minus eta equals that polynomial. If we prove that, then we'll have this symmetry. And but that polynomial, y pi minus, p is a vector polynomial, by the way. It's not polynomial, it has two components. So that polynomial of a degree k0 modulus plus 5 and z. So we need to prove that condition. And when you write them, multiply and write just polynomial, or put 0 on the right-hand side, we need to solve the polynomial equation. And when you count the number of free constants available and number of conditions, it's double. So I mean, we have a number of constants is a half of number of conditions. In general, that, of course, system doesn't have a solution. But again, because of the, it's a not man-made problem, it's a nature-made problem. So there is a beauty behind. So the rank of that system is exactly what we need. It's a number of constant and number of conditions. Even we have a little bit more because we need extra for geometric optic poles. So we have still one constant free. All right, we satisfy these conditions, and now we look at the existence uniqueness. Remember that we had a polynomial, the determinant, it was a rational function of the original matrix, and then we have one Riemann-Hilbert problem, we run the Riemann-Hilbert problem, And the general solutions, again, if you look at them, not necessarily the same, at least at first glance. And we also have different number of solutions for different case. We have total index, we have also indices for the eigen values of the matrix that we factorized. And then that initially was like a conjecture, still conjecture. Conjecture might be too ambitious word, just suggestion or hope that we can, the physical problem has a solution that first independent on the way how we apply Laplace transform, whether we start with a horizontal, because otherwise it's something wrong. And also we hope that it will not depend on the parameters, I mean the number of solutions. And that is why in the paper I wrote that, I call the theorem, but it was probably not. Yeah, anyway, so I said that then extra constant, because of the index, when you have 1, 1, and then eigenvalue has also a big index, then this extra constant are removed by the compatibility conditions between the solutions of Riemann-Hilbert problem 1 and Riemann-Hilbert problem 2. And since they're complicated, that time I was not able to do it. I'm still not able to do it. I actually didn't even look. But the basis for this hope was normal case. If you consider normal incidence when beta equals p over 2, then lots of stuff that we derive for more complicated case are still here. We still have these polynomials. We still have this much between number of solutions for different parameters. And it turned out that if we apply the same idea, now the solutions in elementary functions and in rational functions, if you write this compatibility condition, for instance, when they have negative, negative, it's the case when the number of constant is maximum, then it turned out that identically this solution satisfied if and only if we have a connection between the constant. I wrote only one solution, but there is another Riemann-Hilbert problem solution. And it turned out that regardless where the parameters is, whether we have initially more constant or less, the compatibility conditions always reduce to the same number of free constant, just 1. And the last constant is derived from a Sommerfeld integral representation. When we write integral representation, then we need to make sure that the residue of first potential and second one coincide. I mean, is chosen such that we have a solution that coincide with incident wave, and so basically it's a geometric optics technique, and we fix everything and then write the solution and incident electric reflected waves and diffraction coefficients. All right. Since we're talking about complex analysis, I will skip this stuff. Now, the last problem. It is acoustic diffraction that, as I said, I decided to generalize a little bit what we already found. Of course, the first move was try to generalize it for arbitrary angle, and I spent certain time, instead of just talking to my colleagues, I sat in my office and regret that. But at least something was generalized. I managed to find the solution for exterior of a wedge. So we remind you that, and it's an acoustic case. So of course, for interior of acoustic wedge, it is easy. I didn't mention it. I started with a waveguide, but now we have exterior. So, and how to apply this idea? By the way, similar difficulty arose in Sanasi's focus method. I remember that he said that initially method was designed for convex domains, and then by splitting domains into subdomains, again, which component is convex, he managed to generalize it for, in a certain sense, for convex domains. Here, the same idea. We split wedge into 3 one. So that one, and that one. And but that splitting on its own, I mean, only splitting itself doesn't give, of course, the solution. We need to do something because now it's different. But they are similar. We have again boundary value problem that is basically the same, but on different walls, Laplace transforms. But now we need three unknowns. So basically, one unknown is Laplace transform along the horizontal side, like before. But then we can get rid of Laplace transform along the vertical side, positive side, and negative side along the y. But on the fictitious, like there is no screen, there is nothing. But we still need that function. Impossible to when we match the solution between wedges, we need these two unknowns. That is a Laplace transform of the potential along the negative axis with minus. It makes the function plus, I mean, analytic and upper half plane. And it's normal derivative. So, and that is why we have now a more complicated problem. It is 3 by 3 matrix that needs to be factorized. Of course, you look at it, it's, yeah, you expect more work, but it turns out it's simpler than the previous problem. And I'll explain you why in a minute. So we do actually the same. We need to factorize the matrix 3 by 3. And it has, it is not seen that it has a structure we need, right? Because zeta is everywhere. But if you open the brackets, you see there are only either odd or even powers of zeta. Even power of zeta becomes a polynomial, and odd powers, it's only one zeta, needs to be put aside, and what I did. So you see it is zeta, polynomial matrix 3 by 3. Then again, we remove matrix that we don't want, and we end up with a new Riemann-Hilbert problem. It's a second 2. So we remove, and then we have a diagonal matrix and polynomial matrix. If we just say, well, I want to find, I mean, apply directly the same approach and diagonalize the matrix. If you diagonalize this matrix 3 by 3, I3 plus P, then you will have, of course, diagonal matrix inside like lambda. But this matrix T and T minus 1 will not be so nice as in the case 2 by 2. That zeta will be everywhere in the bottom, in the top, yeah. So that is why we first will look carefully and find the characteristic polynomial. You see it has this structure. That is possible to find the solutions in explicit form without radical. But it doesn't help, as I said, because then this matrix will be not nice. We don't want this zeta be first power zeta or third power zeta in the bottom for matrix T. So that is why we do the following. We look at this polynomial F2, and we want to find not a diagonal structure, but block diagonal matrix. So that is why we look in this operator F2 and analyze the kernel of the matrix operator and find its basis. And the basis of that matrix serves for constructing 2 more columns of the matrix T. So that matrix T now, you see, is nice, polynomial. But it, of course, will not diagonalize the matrix. It will have block diagonal structure. So you have diagonal element and block diagonal. Now, it looks at this matrix. We will do now the same as the matrix gamma in the previous case. And it is possible that hard, long matrix represent in a simple way, like before. And initially, when you look at oh, yeah. So this, I didn't write m and lambda minus L, because initially when I look at them, the degree of this polynomials is long, I mean high. And you would basically be exhausted out from, because you need to deal with polynomials of degree like 10, 12. And initially when I look at them, especially when you have flexible walls, the potential genus was close like 13 or 12, so it just need to stop it here. But so that is why I look first at the constants and found BC. So if at the constants, then mu tilde and mu zero, mu tilde 0 and mu, remind me, mu 0 initially was a function, a rational function. So it's just a constant. And the polynomials still high degree, but for the genus of the surface and for the method, we actually need square root of L square plus mn, and we need only that part which actually multi-valued. So it means that we have a very simple function that is just square root into, so it's genus 0. More complicated, of course, case when we have membranes. Membranes, you say we have high polynomials and so on and so on. And because originally all this m0 needs to be with tilde, which are rational functions. When you design the polynomials at the end of the day, you'll have high degree. But again, if you compute L squared plus mn 1/2, lots of cancellations, and eventually, and all this square root becomes, I mean, this even degrees, and we again end up with a genus 0 surface. All right, so that's my conclusions. But before I just make conclusions, I said that that is probably a hope for solving even electromagnetic wedge for convex domain, concave domain, because I mean for the scattering by right angle wedge, because it looks like all the structure will be preserved, the degree will be higher, but probably even genus will be the same as before. Now my conclusions. So what I discussed 3 problems. For the first problem, I introduce a method which based on this two integral representation Laplace transform and reduced to scalar Riemann-Hilbert problem. Then for school incident electromagnetic wave, I derived 2 symmetric vector problems. Show that for due to symmetry, we don't need genus 3 surface. It's possible to find everything in terms of elliptic integrals. And the last question is what to do if the wedge is not right angle but arbitrary angle. And I didn't look carefully at the focus integral transformation method because it's different. It may help. All right, thank you.
I just would like to ask, there are other functional equations like in queuing system analysis, Cohen-Box, Morphologias, and Gronsky. They also arise to Riemann-Hilbert problems. Is it close to this, no? Their functional equations.
Oh, I cannot comment on that. I don't know what you actually mean, who these people are, and what they derive. So if they derived 2 Riemann-Hilbert problems, I agree. It's all very similar.
It's simpler, but I think it's just you have derivatives and they haven't. But they also do like this. Okay, I show you.
Okay.
Well, other questions, please.
So are there any interesting asymptotic questions now that you have kind of an existential approach that works?
Asymptotics, no, asymptotics is basically the same as expected in diffraction problems. It's actually, if you find something different, it means that you're probably in a different class. But asymptotics at infinity, I mean, the solution satisfies the radiation conditions. Asymptotic at the corner satisfies the.
No, I didn't mean that. I meant something like high frequency asymptotic.
Oh, high frequency asymptotic. As I said, the second problem, it's a paper like almost 40 plus pages. So not everything is done there. So the formulas exact, they more or less ready to be implemented. No numerical solution yet, and still that compatibility conditions not completely. Yeah, so I'm far from. I mean, diffraction coefficients is also here, but no physical results. Yeah.
So just maybe one last question. Sorry about that. So where does the frequency appear if you're doing high frequency asymptotic? Where does it appear in the Riemann-Hilbert problem?
Oh, Riemann-Hilbert problem here is just a tool. We go there, we factorize the matrix, and we come back. So Riemann-Hilbert doesn't appear there anywhere. So it is Riemann-Hilbert problem appeared only in order to factorize the matrix. In fact, it is possible to avoid it and write the formulas, but then it will be natural to ask why you have this solution of factorization problem. So
No, then I did not understand something. Sorry about that. You represent solution of Helmholtz equation in terms of solution of Riemann-Hilbert problem, right?
yes.
That means if you have some high frequency
Oh, you mean Riemann-Hilbert problem, not Riemann surface? I probably misunderstood you.
Riemann-Hilbert problem.
Yeah, yeah. So they appear all that potentials are expressed through the solution of Riemann-Hilbert problem. I probably wrote it somewhere, but
I'm just asking where in the Riemann-Hilbert problem does the frequency appear? So if you're going to do high
frequency is a k. K, it's zeta has k. Frequency everywhere.
Can you show the Riemann-Hilbert problem so we can see where
Oh,
that
sure. They everywhere.
So it's all for regular frequency as well as I understand.
Even formulation.
the fact that it's solved is one thing. Extracting behavior is another thing.
Yeah, you see, for instance, this K0. Yeah, maybe just first start with that. Yeah. K0, it is K sine beta. K is a frequency, actually, it's omega. K is omega divided by C, I believe. It's a, yeah, sound. Yeah, so anyway, K has information about frequency. It's a basic frequency, normalized. And then zeta, of course, has this K everywhere.
Okay, excuse me, so,
Yeah.
thank you very much.